All right, guys, it is good to see you. We are going to go ahead and get started discussing stoichiometry. I believe that this actually means the measurement of elements. I'm not sure though. I did not look it up recently. I will let you Google that and tell me what you find. So stoichiometry. Now, listen. We're not going to write down all the words on the screen. We're going to read the words and we're going to summarize. All right. Plus, I don't know that this definition would really be helpful anyway. Stoichiometry, the mathematics of the balanced equation. All right, now that actually is reasonable. It's the math of the balanced equation. Calculations of quantities of materials consumed and produced in chemical reactions. Hey, it's about the mathematical relationship of what's consumed and what's produced. All right? Someone said earlier, is this the kind of chemistry that's like recipes? And it and it is. This is about cooking and recipes. And so that is. Tell me again. I would say the mathematical relationship between reactants and products, or between any two parts in the. So the mathematical relationship between compounds in a chemical reaction. All right, and it's just a basic algebra. It's the same conversions that we've been doing. All right, let's press on and see what we can learn. There are two types of stoichiometry. I don't know that this necessarily warrants much discussion. Composition stoichiometry and reaction stoichiometry. We're going to be examining reaction stoichiometry. Composition stoichiometry is about the mass relationship of elements in a compound. In other words, this is about if I have an ammonium ion, how many nitrogens and how many hydrogens are there? And how many grams of that is in a mole? So this is about mole relationships and element relationships in one compound. I don't really care that you know all that because we have looked at this. This is about mole conversions, grams to moles, moles to particles, and we are done there. Although we will still keep using those skills in reaction stoichiometry. Reaction stoichiometry is the mass relationships between reactants and products. And that I do care that you know about. That is what we are going to be learning. That's actually a decent explanation of stoichiometry in general. All right, mass relationships between reactants and products in a chemical reaction.
Isn't just baking and cooking basically chemistry? If you think about
Oh yeah, absolutely. Baking and cooking is absolutely chemistry.
Then why would I not cook here though? I mean, it's technically chemistry.
There are different kinds of chemistry and different kinds of cooking. Okay, hey, we don't need to write everything. We need to read it, summarize it. Okay, we need to read it and summarize it. And I will put a recording online, and I will put this presentation online. So don't feel like you have to write down everything. You're welcome. You're welcome. Blessings to you. All right. All right. Hey, so let's think about a sugar cookie recipe. All right. Yeah, this is not a real recipe. Okay, because you need more butter than that. You need a little more vanilla. You need more eggs. All right, and you're sure not getting 24 cookies out of this ingredients. So anyway, but let's consider 2 cups of sugar, 1 cup of butter, 2.5 cups of flour, 1 egg, 1 teaspoon of vanilla makes 24 cookies, and that's in our hypothetical yummy sugar cookie recipe. Do not try this at home, Diego. All right. Now, here's what I'll tell you. This is what it looks like on a recipe card, but this is what it would look like in a chemical reaction. Okay, if we said, hey, 2 cups of sugar plus 1 cup of butter plus 2.5 cups of flour plus 1 egg plus 1 teaspoon of vanilla would produce or yield 24 cookies. And so this is what we see if we look at a recipe card. This is what we see if we wrote it like a chemical reaction. And so you can still think of a chemical reaction very much like a recipe for what's going to go on with when certain chemicals are combined. All right. Now, normally we do not use halves in our coefficients for our chemical reactions. So I would be a little happier if we had doubled all this so that we could have 4 cups sugar, 2 cups butter, 5 cups flour, 2 eggs, 2 teaspoons of vanilla, and 48 cookies. Here's the thing though, the dry ingredients, that much dry ingredients would overwhelm a mixer, so that's not practical. So they had to do a half. But in terms of a balanced recipe, I would really prefer to see it with whole numbers. Diego, no, do not try this at home. This is not a real recipe. Okay. All right, I know. So here is our sugar cookie reaction. And the question was, what is the ratio between sugar and butter? And so you just look and say to yourself, hey, it was 2 cups sugar to 1 cup butter, and so that's going to be 2 to 1. And that's that. Let's see. They are. What is the ratio between sugar and cookies? Okay,
24 and do simplify that, because like it's kind of like a fraction.
that is an excellent question. So you look, and here's what I'll tell you. 2 to 24, most of us would probably go ahead and simplify that to be 1 to 12. I'm actually going to take that one step further and tell you that since they are not equivalent units, that you really ought to include the units also. And you ought to say 2 cups to 24 cookies. You could, and that really is what we would expect to see. Although no, I don't necessarily. You just need to know a correct ratio. It's not necessary to simplify. Okay, and in fact, there will be many times when we will choose not to. All right, let's see what else we had here. Let's see. Let's click that, and click. Oh, if you have 4 cups of sugar, how much butter would you need?
So would you multiply it though?
All right. Well, so here's what I'll tell you. This is a really good question. Would you multiply it? Now, here's the thing. Most of us are going to look and see 4 cups of sugar, and we're going to see that we started with 2, and you're like, oh, that's easy. I could just double it, which means then that I would double the butter from 1 cup to 2 cups. And that's fine as long as it's a nice, easy, 2 cups to 4 cups is a really straightforward doubling translation. And so then that lets you double this one as well to be 2 cups of butter. What if it's not an easy to double? That is when we will use some of our skills from previous units, and we will say, hey, if I start with 4 cups of sugar, you guys know where this is going. Dun dun dun. The grid. And you say, hey, how many cups of sugar are there to how many cups of butter? And you say, oh, well, for every 2 cups of sugar, there is 1 cup of butter. And so 4 times 1 is 4 divided by 2. And sure enough, you would still get 2 cups butter. So here's now, I understand what you're saying. Most people are going to say, but this was so much easier. And that is absolutely true when you're dealing with nice, pretty whole numbers. But what if they didn't say, what if you had 4 cups of sugar? What if, what if the demon came out on them and they said, what if you have 2.78 cups of sugar? Okay. I know. And so at that point we would need to start with 2.78, and we would need to do our grid. And we will practice with that a little bit later. Okay? So what I want you to see is that it's still going to be the same setup in terms of ratio and proportion.
Don't we just have proportions like that? I remember a little bit about proportions.
Well, that's basically what we're doing, except it's not. Except we have to know what our proportion is. All right, let's press on. Oh, I'm going to press the cursor. I am. All right. If you wanted to make 48 cookies, how many eggs would we need? Again, we just look and we say, hey, double, so we would need 2 eggs. Yeah, I'm not thinking that that's going to be enough moisture in these cookies. Yeah, I don't know how much powder and soda we need in sugar cookies, but definitely a couple of eggs. All right, so here is once again our reaction, and it's going to say, hey, ooh, what if I gave you the sugar measured in grams? What would you have to do? Convert it, but convert it from what to what? Oh, it gave it to us in grams, so we would have to take grams and convert to cups. And then we would be able to compare the cups of sugar to the flour, or to the number of cookies, or to the eggs, or whatever. But we would first have to convert grams to cups. Now, there is a similar type of conversion in chemistry, because when you have a balanced chemical reaction, the balancing coefficients actually represent a mole ratio. We're going to talk more about that in a minute, but I'm going to go ahead and introduce that to you. Madison, you look terribly uncomfortable. It's all okay. It's all going to be fine. All right. Hey, you just have, but we don't, if you were asked a question about grams, we don't compare grams to grams. In chemistry, we only compare moles to moles in terms of our balanced reactions. Okay? So the magic always takes place after we convert to moles. You must convert to moles. All right. So let's see what else is on the question mark. Okay, so sure enough, you would have to convert grams to cups, and that's stoichiometry. Hey, so the chemist recipe is the balanced equation. You must always have a balanced equation. If you do not have a balanced equation, you do not have a recipe, you have an ingredients list. Okay? And an ingredients list does not do you any good when you're cooking. If I just gave you a list and said, hey, I would like you to make me some sugar cookies, you will need butter, flour, salt, sugar, eggs, vanilla. And you're like, but how much of each? And I'm like, oh, you pick. Okay? That's not going to go well. Those cookies are going to be terrible. All right? 12 eggs, 1 cup of flour, 17 cups of sugar. All right. And all the butter. And then stir. All right. Hey, the point is, you must have a balanced equation so you know how much of what goes with how much of what. Now, in this case, we've got 4 ammonia molecules, plus 5 oxygen molecules makes 6 water molecules and 4 nitrogen oxide molecules. Hey, take a look at a couple. First of all, let's check and see if this is balanced. 4 nitrogen, 12 hydrogen, 6 times 2, 12 hydrogen, 10 oxygen, 6 oxygen, plus 4. 6 plus 4, ooh, that was close, 10 oxygen. So it is, in fact, balanced. Let's put a little check mark by that. Here's what I want you to see. In this case, this is not cups of ammonia. This is moles of ammonia. And remember, we don't always have everything in equal amounts in a recipe. You have more of one thing and less of another. in this case, 4 moles of ammonia would mix with 5 moles of oxygen to produce 6 moles of water and 4 moles of nitrogen monoxide. Okay? Questions about that? All right. So let's see what's next. Oh, if you have 8 moles of NH3, how many moles of water would you produce? So again, I can look at this, and this is a nice clean number. 4 to 8 is going to be a doubling. So again, 6 will double to, that's correct, 12. And so we will have 12 moles of water produced. What if we had 8 moles of ammonia? How many moles of oxygen would we need? Again, 4 doubling to 8. So 5 oxygen. You always have to look at what you're asked for. 5 would double to, yes, 10. Okay, but what? Okay, you would. That's an excellent point. So Diego, what we would do is we would not actually change the coefficients. We at that point are simply, it's kind of like if we want to double the recipe. If we want to double the recipe, you've got to double everything. But you don't actually change the recipe.
So it's more like an implied.
You're just talking about we're just doing calculations with the amounts.
So you don't change the subscript?
You never change a subscript. Once you have written your correct chemical equation, we never change the subscript. It is hands off the subscript. Okay? And the only time you change the coefficients is when you're balancing. So you write the subscripts in order to write the equation correctly, meaning the chemical molecules and the compounds. And then you write the coefficients in order to balance correctly. But then once you have that done, you use that recipe to make calculations. You don't change the recipe from that point on. So I'm not going to change my 4 and my 5. I'm going to say, hey, what if I had 8 instead? And again, this is where I like to write. What do I have? 8 moles of NH3. And again, if you're uncomfortable with the grid, you can multiply by a conversion factor. Remember that a conversion factor in this case, if we don't want to change the value of this, it needs to be equal to 1. And so we need to put equivalent things over each other. So I'm going to put moles of NH3 on the bottom. I want to convert to oxygen, so then I'll have moles oxygen on the top. And let's see, it looks like that is a 4 to 5 ratio. And so sure enough, 8 times 5 divided by 4 would end up equaling 10, just like we had thought from our simple doubling earlier. So whether you use the grid or whether you use separate conversion factors, they mean the same thing. It's just whichever one you're most comfortable with. All right. Questions so far? All right. Let's press on. Sure enough, 10. Yay, thank you. Ooh, what if I gave you the ammonia in grams? What would you have to do? No, we always, because remember, we always make our comparison in moles. And so the first thing we would do would be convert grams to moles. And then, honestly, Diego, we would have to look at what else they asked us. If they asked us for a final product in grams, we would go grams to moles, moles to moles, and then moles back to grams. And so we'll that's going to be our ultimate goal, is to be able to do things like that. To say, hey, what if I gave you 85 grams of ammonia and excess oxygen? How many grams of nitrogen monoxide could you expect? And so that's what we're ultimately going to be looking at trying to figure out. Yes, ma'am. No, just stretching. Okay, excellent. All right. So let's see. Convert grams to moles. All right. So there's our ratio once again. Ooh, I want everybody to just take a good look at this. Stoichiometry is really going to be about if you started with a certain amount of A, how much C would you end up with? Or if you started with a certain amount of A, how much B would you need in order to be able to complete the reaction? Or if you made a certain amount of C, how much D could you expect as well? So these are the kinds of questions that we'll be answering. And it works the same way, again, it works the same way in real life in your kitchen. My family came over to my house Saturday night, and we had chicken quesadillas. They were wonderful. But before my family came, I said to myself, okay, there's going to be 6 of us who are going to eat quesadillas. That means that we will need this many quesadillas, which means we will need, this many tortillas, this much chicken, this much. Okay, but it's all based on, a recipe of what goes into making one quesadilla. And then how many of those do I need for each person, and how many people will I have? And so stoichiometry is something that you do all the time. It's just that you haven't necessarily applied it to chemicals. And that's what we're going to be working on doing now.
Well, we did apply to chemicals, aren't those chemically chemicals?
Possibly. I don't know. We'll have to think about that. We'll have to think about the definition of a chemical in that sense. So let's review a couple of things. First, here's our balanced equation. We checked it earlier. And this is going to remind us a few things about balancing equations and how to check the compounds. If I give you an ammonia, how many nitrogen and how many hydrogen is that? 1 nitrogen, 3 hydrogen. What about oxygen? 2 oxygen atoms. Water? 2 hydrogen and 1 oxygen, excellent, and then 1 nitrogen, 1 oxygen atom. Good. None of that was a surprise to any of you guys. Ooh, how would I calculate the molar mass for ammonia?
Don't you just look up the atomic mass?
Well, I would look on the periodic table at the atomic mass, or at the and I would say, hey, nitrogen is 14.01, hydrogen is 1.01. 1.01 times 3 is 3.03. Add that in, and you get 17.04. And it's grams per mole. So 17.4 grams of that per mole. We would do the same thing for oxygen. Hydrogen. Yep. Or nitrogen monoxide. All right. But remember that these are our molar mass conversions that we'll need to convert moles to grams or grams to moles. And so just remember that that's how we get those. All right, and once again, when we look at a balanced equation, so again, how to balance equations. 4 times 1 is 4 nitrogens. So that's why, of course, we had to put the 4 out there, was in order to balance the nitrogens. And so 4 nitrogen, 12 hydrogen, 10 oxygen, 12 hydrogen, 6 oxygen, 4 nitrogen, 4 oxygen. Ooh, I know. Got me. So watch out for that. Don't be a victim, all right? Reaction stoichiometry. And here's getting into the stoichiometry part of reaction stoichiometry, is looking at a balanced equation and saying, so how many moles of this do I need to make how many moles of that? Okay? And so it's about that balanced equation that tells us the ratio between the reactants and the products. Now, I do not like writing it this way with just the numbers, and that's because really these could be in either place. It's just as correct to say 4 moles of nitrogen monoxide plus 6 waters. Okay, so it's just as correct to write it either way, and that of course would change these two numbers. So I don't like writing it that way with just numbers. I prefer for you to write a full balanced equation, unless you're given the chemical compounds in a certain order, and then you could write just the numerical ratio. How many ratios can you find in this reaction? I'll give you a first one. 4 ammonia to 5 oxygen. How about 4 ammonia to 6 water? Or 4 ammonia to 4 nitrogen monoxide?
16.
Okay, there won't be 16 because you've counted some duplicates in there. Yeah, there's more than I'm going to bother to put on the screen. I think clearly there are at least 6. Let's see. 1, 2, 3, 4, 5, 6. Yeah, I think you're right. All right, so there we have it. Good job. Hey, we're gonna explore a new conversion factor. It's not really new. It's moles to moles. And where we get this is where we're going to compare the number of moles in one compound to the number of moles in another. And I've drawn this on the screen a couple of times already. Let's see, if I just click back real quickly. Hey, how many moles of water go with 4 moles of ammonia? Or how many moles of ammonia to how many moles of water? How many moles of ammonia to how many moles of water? 4 to 6, yes. And so that's going to be our conversion factor here. It would be like 4 to 6 or whatever to whatever, depending on which two chemical compounds you're comparing. All right? And you pull your ratio from your balanced equation. We've used grams to moles before. We've used moles to particles before. We have not used liters and moles before. I will tell you about that in just a moment. Grams to moles comes from the molar mass from the periodic table. Moles to particles or particles to moles comes from Avogadro's number, the fact that you have 6.02 times 10 to the 23rd of anything in a mole. Liters to moles involves the volume of a gas and the moles of a gas. And it comes from the conversion factor that all gases will have 22.4 liters of gas in 1 mole of gas at standard temperature and pressure. If you change the temperature or if you change the pressure, you would get a different.
So can you list an example where we might need this liters to moles thing?
Well, anytime that you're working with gas conversions, and that'll be what we'll do. We'll sort of introduce that this unit, and then we'll do more with gases next unit.
Why would you convert gases? Like, why would somebody work around,
Well, we do a lot of chemistry with gases rather than only with liquids and solids, and so that's going to be where we would make use of that.
So we're dealing with how gas tax work by that? Can we learn about that or no?
How gas what works?
Gas tax, like chlorine, like we just
Oh,
learned about chlorine. Like we just learned about chlorine class in history, though.
right.
And how like it filled up
We-
with ozone.
Right. We probably won't learn the specifics of that. We'll leave that to your history class, but we will learn about chemical reactions involved. All right. Hey, this little graphic ends up getting quite. Everybody, take a look at this little fella on the screen. This graphic is very straightforward, but in just a minute I'm going to click some more things, and it's going to get rather crowded and confusing looking. I want you to follow along with me and not be confused. Okay? So everybody follow along. And here's what I want you to know. You can take mass of a chemical and convert to moles. You can take number of particles and convert to moles. You could take liters of gas and convert to moles. Okay? Any of this could be turned into moles. All right, and that's what you have to do. That's what we've done previously. If we had 47 grams of something, and we wanted to know how many particles that was, you can't make that transition directly. You have to go through the mole and then back. All right, and that's still going to be what we do, except now we're comparing one type of chemical. Okay, so I'll just write compound A. And we are going to compare that then. There we go. Of course, remember that the way that we convert our mass to moles is through the molar mass. The way we convert the particles to moles is through Avogadro's number. And I just told you that liters to moles, liters of gas to moles, goes through 22.4 at STP, standard temperature and pressure. So if we have this much of compound A, we will then use our moles to moles ratio. If our given is compound A and our unknown is compound B, then we would use our mole ratio from our balanced equation. Whatever we were given, we would convert to moles. Then we use our balanced equation to convert from moles of A to moles of B. And then we take compound B and convert backwards to whatever we were asked to solve for. Maybe it was mass, or maybe particles, or maybe liters. Okay? So again, let's say that you started with grams of something and you were asked to finish with grams. You would go grams to moles, moles of A to moles of B, and then moles of B to grams of B. Okay? Hey, do we see how that's going to work? It's this one graphic that we've been using. Okay? Grams to moles, moles to grams, particles to moles, moles to particles. And then we haven't done this part before, but it's there. It's taking this graphic that we've already been using and using it for two types of compounds that are related through the balanced chemical equation. Yes, yes? All right, excellent. Hey, questions? No? All right. Questions? No? Okay. Well, let's see what we got then. Ooh, no, sorry. For moist stoichiometry, no. For most stoichiometry problems, moist stoichiometry, no. Most stoichiometry problems. First thing you always ought to check is balance the equation. Sometimes you might have to write the equation and then balance it. Other times maybe they give you the balanced equation. Don't trust them. Check it. Okay, you have no idea who they are and where they came from and what they were doing with that equation before they brought it to you. Okay, you always check that balanced equation. All stoichiometry problems must begin with the balanced equation. Write that down. Okay, this is worth an asterisk and a star and some arrows and some more stars and some circling, some underlining. All stoichiometry problems must begin with a balanced equation. Must. Then you have to back up and balance and get a balanced equation before you can go any further. If they do not start there, then you have to make them start there. All right? Arrows asterisks, stars, circles, boxes, underlining. We want it all types of emphasis. All right? Highlighting. Yes, ma'am. No, you don't have to. You definitely need to write that stuff down there at the bottom, though. All right, we are pressing on. All right, so let's try this one. Now, we have already checked this one. It is balanced.
Are you sure?
Yes, because it's the same one that I checked originally that we've been using for like 12 slides now. So I am certain. How many moles of water are produced if the reaction begins with 7.5 moles? Ooh, this is that thing that I was talking about. It begins with, and this is not a nice, easy, smooth number that you can just say, oh, 4 to 7.5, we've doubled it or we've tripled it. And so we will have to use our ratio. Let's see. All right, I will let you direct me. Let's see. Let me. Yeah. Okay. So tell me what to do to start with.
So you have to draw like a little board, the graph,
All right. So we'll start with our grid.
right? And in the top left, you like 7.50 moles of NH3. And in the bottom right, you would write moles of NH3 since we don't know what the
All right. So down here, I'm going to write moles of NH3 because we know that we want my moles of NH3 to divide away, and so we want them on opposite sides of the division bar. Go ahead. Doing great.
and then at the top it would be moles of H2O since we want to get water.
We would like to get to water because it says how many moles of water. So this is what we're trying to get to.
And then at the bottom would be 4 moles of NH3 and 6 moles of H2O.
All right, our mole to mole ratio, we have 4 moles of NH3 for every 6 moles of H2O. And so we'll assign those mole ratios correctly for that. And then 7.5 times 6, and then divided by 4. And you should, in fact, get 11.25 moles of water.
Yeah,
All right. Love it. Good job.
thank you.
All right. I'm going to erase your excellent work and click through, and I'm just going to keep clicking because this does exactly the same thing that we just did. Oops, except, oh,
That's a curveball, man.
what? 11.3. Well, we put 11.25. Isn't that the same?
No, because
Oh,
significant
significant figures. There are 3 sig figs, which means that we need our answer to have 3 sig figs. I know. Hey, 11.3, still excellent work. And I dare say we've learned something. So 11.3 with our significant figures, erase and bounce on. 3 sig figs in the given, 3 sig figs in the answer. Someone asked me previously, why do we not just use 1 sig fig? Because this actually has an infinite number of significant figures because it is an exact conversion ratio. Okay? And so because it's exact, we do not limit ourselves based on it.
Question, Mr. Willis, if we simplify that fraction, though, would it affect our answers or no?
It would not affect our answers. I'm going to ask you not to simplify it, though, because you can still see it in the balanced equation. And you never know when you might have to work with something else at a later step if you had more than one step. So I'm going to tell you not to simplify.
Okay.
All right? Yes, ma'am?
What do you think of this?
7.50, this is a non-zero number, and so it is significant. This is a non-zero number, so it is significant. And this is a 0 at the end of a number following a decimal. And so that makes it significant as well. And so there are 1, 2, 3 significant figures. All right? I would encourage you all to review your significant figures rules just so that you can kind of be familiar with those. And if you need help with them, let me know, and we can just spend a couple of minutes going over those one day. All right, let's press on here and see what else we can work through. All right, here once again is our famous example problem. If 25 moles of water are produced, how many moles of nitrogen monoxide will also be produced? All right, hey, so see what you can do with this. I'm going to begin to work, but I'm going to ask you to work along with me and see if you can. I'll be slow and see if you can outlast me or outpace me. 25.0 moles of H2O. I actually write the first one before I draw my grid because otherwise I sometimes don't leave myself enough room and I have trouble squeezing it in there. All right, so remember, first thing we check and see if it's balanced. It is. Next first thing is we start with whatever we were given in that upper left corner. All right, and then keep going and finish and do your math and get your answer. So moles of H2O to moles of nitrogen monoxide, and let's see, 6 moles of H2O to 4 moles of nitrogen monoxide. So 25 times 4 divided by 6.
I got 16.6 repeating, so it would be 16. Because it's only, and then after the decimal place, the 0 counts, right?
The 0 counts since it follows a decimal.
So it'd be 16.7.
Love it. Good job. All right, let's erase and click and see if they got the same thing. Erase. Click. All right, mole to mole ratio. Boom, 16.7. Good job. And again, 3 significant figures in the given and in the answer. All right. Okay. Hey, let's do this one. Magnesium reacts with hydrochloric acid. Okay. So magnesium and hydrochloric acid. So we need to first write down our equation. Magnesium plus hydrochloric acid. At that point, this is looking like a single replacement reaction. I would check my activity series, and I would find that magnesium is more reactive than hydrogen. So that means that it will replace hydrogen. And so we will get magnesium chloride. Now remember, magnesium is a +2, which means I'll need 2 chlorines since they are -1. And hydrogen gas, which you remember is diatomic, and so it goes in pairs. All right, now take a moment and balance. Magnesium to magnesium, hydrogen to, whoops. Oh, all right, well, that was easy. So what we see now is that 1 mole of magnesium plus 2 moles of hydrochloric acid will produce 1 mole of magnesium chloride and 1 mole of hydrogen gas. So now we are ready. Now we have our balanced equation. We have our recipe. We're ready to actually write down and work our problem. 7.80 moles of HCl. Now, let's see. Moles of HCl. And we have to go moles to moles. What does it even ask for? It asks for magnesium chloride. We always have to go moles to moles. 1 mole of magnesium chloride for every 2 moles of HCl. And when you divide that, you will get 3.90 moles of HCl. Or excuse me, of magnesium chloride. Yeah? Except it wants grams. Dun dun dun. So we need to go one more step. I think this warrants a different color. All right. And so now we need to get rid of our moles of magnesium chloride. And we need to get that into grams of magnesium chloride. All right. How many grams of magnesium chloride are there in 1 mole? How would we know? Look at the atomic mass. Yes. What is the, let's see, chlorine is 35.45. Okay, because we are going to pull, I told you to, anytime you're pulling a number off the periodic table, to pull 2 decimal places. We're not going to care about significant figures. In this case, we're just going to say pull 2 decimal places. Let's see, the magnesium is what number? 23? 23 point, 24.31. Okay, so 24.31. Let's just make a quick change. And of course we have 2 chlorines. So combine all that together and tell me what we get. All right, I want us to recheck that. I think it should be in the 90s. So 1 magnesium and 2 chlorines. Everyone punch the numbers. All right, so 95.21 grams per mole of magnesium chloride. So I'm going to write 95.21. All right, now do the math. 7.8 times 1 times 95.21 divided by 2 times 1. So just divided by 2.
371.32.
All right. What'd you say? 371 point?
32 grams per mole.
Well, what's left?
I got this
Grams of magnesium chloride. All right. We're so close here.
Yeah, it is. Oh, so okay, so it'd be 371.3. 371.
You got to go with the smallest one. Hey, that's okay. What an opportunity to refresh and and be dominant on them now. All right, and so that would be 371. All right. Let's see. We are going to pause our recording there. Thank you guys so much for watching today, and I hope you have a great afternoon.